Okay, so we are about to start. Before we start, can you just guys introduce yourself, or what do you work on, and why you're here? David, maybe you start first.
My name is David. I work on render forest. I'm not just developer. I have previous experience of C++ for about 5 years. Now this last 1 year, I started to learn JavaScript, especially in JS, and I am also doing my PhD. I have signed papers in international, and that's it. I've also been a lecturer for C++. So,
Next person,
I'm Ashot. I'm a student.
speak up louder.
I'm a student. I'm studying at Vienna State University, master's degree. I love C++. I don't work yet. And it's fun.
I'm also program. I'm software engineer from Nitrographics. I initially worked on Nitro project, and after that, Calibre project. Right now, I'm working here.
Okay, go ahead.
Hi, I'm Armenia. I am software engineer, C++.
Got it. So, just out of curiosity, who of you know what is SIMD? SIMD, SIMD? No one? Okay. So, do you know what branching is? Okay, so there will be some new content here, but SIMD is kind of related to branching in some ways, not directly. But anyone who's following us online can open up this repository on GitHub. Most of the code is available there, and we'll go step by step through what is SIMD and how we can achieve superior performance in new applications. But before we start, here's who I am. I've been programming my entire life as much as I remember myself. I started by doing web development online sometime in elementary to middle school. And then when I grew older, I started doing mobile development in high school. I had a couple of relatively successful businesses. Then I started doing astrophysics for a few years. Then I got bored with astrophysics, so I moved back into research, and I was designing my own algorithms for big data processing and AI. And this is how I got on track to build Unum, a framework that I've been working on for the past 5 years. So it's a big piece of research, but while I was working on it, I also wanted to have some fun. So I traveled all around the planet. I've lived on every single continent. The only place I haven't been to is Australia. And in parallel, I was developing this piece of software, and some parts of it we'll actually see today. I'm curious about all kinds of computing, starting from analog, electrical, and finishing with quantum. So we can talk about all of this together and how this can merge in one single piece of software. But given that we talk about C++, and C++ is a language for most electrical systems, so this is what we'll talk about. Now, this is a glimpse of what can be achieved in theory using SIMD instructions and low-level assembly. So once C++, pure C++ is not enough for your performance numbers, for your performance goals anymore, you go down one level to assembly, and this is where the true magic happens. So within Unum, the framework that I've been building for the past 5 years, I have a lot of different parts of the applications, but those parts of the applications build up on smaller pieces of infrastructure, such as basic data structures, basic algorithms, such as std-set, std-unordered set, some databases like Postgres. And I didn't have too much money, but I had insane goals. So I wanted to process the whole data of the universe on a single computer. So I wanted to design the most efficient solutions for every single problem. That's how I started, by optimizing them with SIMD instructions and assembly. So if you just design a lookup table to check if something is within a set or not, and you use std-unordered set, which is about 3 to 4 times faster than std set, you still get about 150 nanoseconds delay for the lookup time if you have about 1 million to 10 million elements within your STD unordered set. If you have lookup heavy operations such as analytics of whatever kind, you can design something like what I designed and you will get down to 15 nanoseconds. So essentially what was a bottleneck in your applications will stop being a bottleneck. And this is something very, very low level, like generating random numbers at 12 gigabytes per second. But this composes into much higher levels of infrastructure. So regular expressions is something much more complicated, and STD regex uses some other libraries under the hood, so it's not a pure C++ implementation of regex. I was able to achieve about 10 gigabytes to 14 gigabytes per second performance. With Postgres, I needed to do a lot of scanning over my data. So I collect some data and I want to do AI on top of it, but I cannot do fast scans over slow databases. So I had to design my own databases for this. And my database provides me with a stream of 2 gigabytes per second from disk, sorry. So this is kind of close to the theoretical limit for PCIe bandwidth. But this is like a very broad set of topics. Let's focus on something very, very trivial, some specific application that every single one of you is familiar with, Substring Search. So let's take a big chunk of letters. We'll call it the haystack, and we'll have to find a small needle within this huge haystack. So an example can be, let's say, a text with 10 million letters in it, and we have a small word with just 5 letters, and we want to find every single inclusion of this smaller word into a bigger text. And this is what we'll work on today. And for reference, if you just try to implement this in Python, you will get 10 megabytes per second search speed. So essentially, you will be able to process 10 million letters within the haystack, comparing against the 5-letter needle. And this is kind of slow, because if you have 10 million letters in your text, it will take you an entire second to find all inclusions of this smaller word in a bigger text. With C++, if you write your code nicely, you can get to 2 gigabytes per second. But with SIMD instructions and assembly, I get to 12 gigabytes per second on a single core. And at this point, the algorithm becomes not compute bound or CPU bound, but memory bound. So the DRAM memory just cannot supply you with enough data.
What is SIMD? Is it just a language or?
Right. So we'll get to this. So originally, this talk was prepared for like a very trained audience who already know what SIMD instructions are. So this is basically the next step of what you would do. But for like people who are not familiar, I can introduce the very basic things. So essentially, C++ is a higher level language, which means that it's platform independent. So if you take the Intel CPU and the ARM CPU, if your code is standard C++, you can compile it to every single architecture. Assembly is a different thing. It's a lower level, so it's specific to every single platform. So there is a custom assembly for x86, there's custom assembly for ARM, but the compiler will essentially do most of your work translating your higher level language into the assembly for you. But what if you don't want to let the compiler do whatever he wants to do and you want to write your assembly yourself because you think you can do a better job than your compiler? And most of the time you will be wrong because compilers are very smart these days. But sometimes, if you know what you're doing, you can get from 2 gigabytes per second to 12 gigabytes per second. And this is like a very broad lecture. I hope everyone will get something new out of this. So it will start with very basic things about what are the small building blocks of assembly, and into the more complicated parts. But assembly is just like essentially language. It contains all kinds of words and instructions that the CPU can do. But the past 10 years were different. As the CPU vendors such as Intel and AMD and ARM, they couldn't increase the frequency of the CPUs higher and higher. So almost all CPUs these days are somewhere between 2 and 5 gigahertz in terms of the operating frequency. They started to design new kinds of parallelism to do different operations in parallel. So the one obvious example is multi-threading. When you have a CPU with 4 cores and maybe 8 threads, it means that in theory, 8 operations can run simultaneously on every single core. But there is another level of parallelism just below the multi-threading, and this is vectorized instructions. So what if you could tell your CPU, not just take this number A and this number B and sum them together? What if you could tell him, take those 8 numbers, A1, A2, A3, up to the A8, and the numbers from B from 1 to 8, and sum them pairwise? So essentially, SIMD stands for single instruction, multiple data, or in other words, assembly instructions that can process more than one piece of data at a time. So essentially, not only your cores can work simultaneously on different pieces of data, but also within a specific core, you can do more than one operation per cycle, per CPU cycle. And we will talk essentially about doing the brute force approach of naive substring search, and then how you can use some kind of interesting heuristic to make this operation much easier and much faster for the CPU. So there are specific terms, and there's a lot of confusion between those terms: mnemonic, intrinsic, and instruction. Let's unveil the mystery. So a mnemonic is just question again.
So it's not just assembly language.
It is part of assembly,
but with multi-threading support.
Not multi-threading support. It's within a specific thread. Yeah. You can do more than one work. So essentially, you can have, let's say, 8 cores. Each of the 8 cores is working on 8 different problems, and every one of the cores is also working on 8 pieces of data within that specific problem. So essentially, going from single threading to multi-threading is 8-time performance improvement, but also going from simple assembly to SIMD assembly is 8 times improvement within a specific thread. So you get 64 times higher performance if you combine those 2 techniques together.
So you can run on each core processor, you can run some different programs.
You will run the same program, but you will work on, let's say, different pieces of data. So as I told you, it stands for single instruction, multiple data. So you can apply only one same instruction to 8 pieces of data at a time, for example, within a specific thread. You cannot just say multiply first 2 numbers and then add the next 2 numbers and then divide the next 2 numbers. All of them have to be working with the same kind of operation, but it will happen in a vectorized way, and the modern CPUs support this. So there are specific terms that you need to know. The first one is what is mnemonic. A mnemonic is just the name of the operation, like add, multiply, move memory from this part to this part, copy something. And intrinsic is like the core of this talk. Intrinsics are special names, or we can call them names for those SIMD assembly instructions that you can call from your C and C++ code. And your compiler, such as LLVM or GCC, knows how to replace those kinds of intrinsics with an assembly instruction. So you don't even need to know assembly itself. You can just combine C code or C++ code with intrinsics that look like C, but essentially are compiler hints, and it will do the rest for you. And instructions are the final result. So essentially, a compiler will take an intrinsic and replace it with an instruction. But we can decode this intrinsic signature and kind of see that it looks like more like a C function. So we have the return type, we have the name of the function call, and we have 2 arguments. The M256I stands for using a CPU register that is 256 bits in terms of width. So not 32-bit numbers, not 64-bit numbers, but whatever bits you have that fit into 256 bits. Then with prefix, then we have the name of the function call, and this has a similar ABI to C, or not even ABI, but it has similar signatures to C. So they have prefixes for the kind of for argument type resolution, because you cannot do argument overloads in C, only in C++. So we prefix with 256, saying that we need a function or an intrinsic that works with 256-bit data points. Then we call the operation, and we essentially provide the short name of the mnemonic, which is CppEQ, compare equality. And then we pass the 2 arguments. So what this will do, it will take 2 256-bit buffers, and it will run compare equality operation, or essentially the double equal sign operation, between every 32-bit part of a 256-bit buffer. So essentially, if we divide 256 by 32, we end up with 8 numbers that fit into every single one of the buffers, and we will compare them pairwise. So what we'll end up with is another buffer with 256 bits, and every 32 bits out of those 2056 out of the return object will contain just only full ones or full zeros, depending on the equality result. So if it equals, then we have all ones, essentially the maximum value of a 32-bit unsigned integer. Or if it doesn't match, we'll have all zeros, which is a 0 unsigned integer. So enough with the basics. Let's do the substring search. Hello, guys. Are you for the C++ meetup? You've missed the intro part, but I hope you will not get confused with the rest of it. So let's do substring search. Yes.
Where are these SIMD functions defined? They are not standardized yet, as far as I know.
So they are standardized by the compiler, but not by compilers, but by hardware vendors. So I'll provide the links at the end, but you will be able to open the Intel website and the ARM website and look up all the available mnemonics and intrinsics for whatever operations you want to optimize. So it will never be part of the C++ language, or maybe it will be, but not fully.
Proposal, I think.
STD, SIMD.
But I didn't.
Yeah, but it's very constrained. So they will never implement all the SIMD instructions. I guess it will be easier from there, like from the top. But even if they introduce STD, SIMD, it will be just a very small part of available SIMD instructions. And there are about 5,000 of them, so it's a lot to cover in the standard. Yeah.
So there is a difference between C++ equality operator and this one, yes?
Because in a way that the simple one operates on scalar values, so you operate on single elements, and this one operates on 8 elements at a time. So we'll go through the examples, and maybe they will show you a better picture of how it works. So first of all, let's just take up the equality operation. I guess this one is familiar to everyone, right? No problems here. If we implement this equality operator as some kind of a function call, we can write it like this. So we take two string views. We first check for the equality of size. If the size is equal, then we compare all characters within those strings pairwise. And if all of them match, then we have a matching string. Matching pair of strings. So we'll go through the loop until the size of the strings. We compare the elements pairwise and we return false if they don't match. Who thinks there's a problem with this code? There are many problems with this code, so go on, try yourself. And to make you a little bit more interested, we have bounties for those who can spot the problems with this code.
Problems like performance or like?
Well, obviously not style guidelines, but performance or quality or something like that. Just go and try yourself.
Passing by value, A and B.
No, this is actually a good guideline. So if you are passing std string, it will produce a heap allocated copy. But if you're passing a string view, this is just 2 pointers on the first character and the second character. So actually passing by value is good value semantics. You should remember and do like this.
Size function for A is called twice.
Yes, it can be better, but this is not the worst part. So calling the A size is essentially taking 2 pointers and subtracting one from the other one. And simple integer operations on 64-bit integers are the simplest, fastest operations on modern computers. They take 1 CPU cycle and they have no other latency. Yeah, go on.
Without taking into a string view implementation, maybe there are some functions which throw some kind of exception.
No, std string view is very lightweight. The problem is not really in std string view.
Why you use indexation operator? You can use just pointers with increment.
Yes, that is better. But there is also a bigger problem here. And like the next bounty will go to one who can spot it.
There are too many code paths. Maybe.
Code paths?
We have too many branching.
Yes.
Branching.
The keyword of today's presentation, branching. Elaborate on this.
For example, we can get rid of the first check. I think we can check it in the end, like make it
Which one? This,
Size check.
this one?
Yes.
You are very close. You'll get the bounty for trying. But let's analyze. We have a string view that is, let's assume we have two strings. Each of them have 1 million characters. The first if will be called once, no matter what strings we pass in. But if we have 1 million characters, we will have one if statement inside the for loop over here. So if I is smaller than a size, and we'll check it 1 million times until we fail. And the second time here, we'll check it also 1 million times until we fail. So if we pass two strings with 1 million and 1 characters, and the first 1 million is the same, but the last one is wrong, then we'll essentially have one if statement here, 1 million if statements here, and 1 million if statements here. And branching is the worst thing you can do to your computer. Like, if you hate him so much, tell him to do branching all day long. So modern computers do what is called speculative execution. And this is the core part of this talk. Speculative execution and how to avoid it, how to reach maximum performance. What it tells us is that a computer not only can work on multiple things simultaneously, but it can look ahead of what is coming next, what kind of problems it will have to solve in the future, to maybe rearrange the operations in some better way, so that it knows how to do it better at runtime. But if you put branching, just like after every second operation, it creates confusion for him, because he doesn't know to which part of code to jump next and which operations to do next. And this confusion and this uncertainty is what will diminish all of your performance metrics. Like, you will never reach them if you leave this branching. So what do we end up with? If we have a string, if we have strings of size n, we'll end up with 1 plus 2 times n if statements. And never forget this one, because there's an if statement in every single for loop. A for loop is just an if statement with a go, or go to, sorry. Yeah, the keyword that is never used in the modern code, but it's like the most essential one.
One problem.
Yes, go on.
And what about every time about a size invoking this member? Maybe there's.
We'll replace it, on the next slide. Yes.
One moment. Maybe there are multi-threading, and some thread changes this size. But every time.
It cannot change this.
Every time this tickle.
This will never happen because we are passing by value. And as we pass this by value to this thread, other threads have no possibility to update this variable, because this lives on the stack of this current thread. If we had std string const reference, then yes. This is why I'm telling you, remember string view, remember std span, and always use value semantics in your code, especially high performance code. This is like the good guideline. Okay.
But every time this a size.
Actually, like almost every single compiler will take a size out of here, put a separate variable over here. And if you look into the assembly code, this is optimized away, but this it cannot optimize away. This is what we can end up with, how we can optimize this. We can take I as a separate variable, and we can go through our array character by character and essentially merge together the second and the third branching part. And essentially we'll only be incrementing I as long as the size is, as its index is smaller than a size, and until we are within matching part of the strings. This may look a bit confusing to people who haven't tried like doing hardcore HPC stuff, high performance computing stuff, but this can save you like some performance. So especially if you're using some old compilers. So this is the trick number one that we should remember and maybe use in your code. Just if you can merge multiple if statements, multiple levels of if statements into one single statement, do it. But we can go beyond. We can actually eliminate this part, eliminate the lookups, and just use char const pointers, increment them one by one, and as long as the value at this memory address is matching the value at another string's memory address, then we are all fine. And the strings match if only our iterator or a pointer, which is a pointer at this point, has reached the final end. So essentially 2 strings match if this for loop has gone until the end and didn't find anything. Okay, let's use those pieces to develop something. So there is this basic string view class, and std string is just instantiation of basic string with basic chart type. Let's design two parts: the engine, which is the top right, and the loop, which is the bottom right. Essentially, the purpose of the loop is to use some kind of engine which finds the next inclusion of a substring, not all inclusions, but the next inclusion of the substring in the given string. And the loop will basically take the big string, find the next inclusion, return it into some kind of other variable or save it, throw back the part that we've already analyzed, and pass the remaining back into the engine. So essentially, the purpose of the loop is just to use this engine that only can tell the next one to actually highlight all inclusions. And we've designed a very basic, naive implementation of this search using the std_strings.find function call. It's over here. So we can pass another basic string or basic string view into the string, and it will use whatever is already implemented in the standard templates library. So using this, we end up with this single line, which is size t offset is equal to haystack stl.find needle stl. So we've converted whatever span type we had into this STL compatible format. We pass it to std_string.find, which is over here. And if the result is not non-position or null position, we return the offset that we found. So what we can do next with this? Let's design the same thing, but ourselves, without using the std_strings naive.find implementation. So we'll essentially try every single offset of a bigger string. So essentially, we'll have our needle, and we'll compare the needle against the first letter in the input string. If it matches, we'll compare it to the second. But if it doesn't, we shift the haystack one character right, and we compare there. So essentially, this is a brute force algorithm trying every single combination. So we try every single offset, and we use our function that we've just developed to compare the R equal of the haystack plus the offset at this point with the entire needle. What did we achieve? So in order to provide you with the best results and like the most complete data, I've actually partnered with guys at Intel. We've been thoroughly benchmarking different algorithms like this on their servers, mostly in Russia, at Intel's lab, on my personal laptop, which is right here, and also on some IoT devices, such as the Jetson NVIDIA board for AI. So if you do the same thing in Python, across devices, you get 4 to 14 megabytes per second performance on a single core in terms of matching the string. If you use the STL's std_strings.find method, you will get something between 560 megabytes per second and 1.2 gigabytes per second. But if you use our naive approach, you get even less than that, which is about 1 gigabyte per second.
Which Jetson do you use?
Jetson AGX. Okay, done with the talk, now we can go home. But obviously no, because those numbers are even worse than the standard. If this was the end result, we didn't even gather, we wouldn't even have to gather here. Like, there's no point in designing something that's that shitty. So let's design something better. And let's do this simple thing. So one of the most complicated parts of our for loops here in our naive approach is that we do this inner for loop for every single offset of a bigger for loop. And for loops are expensive because there's a lot of branching, there's like complicated machinery that is involved. What if we knew the size of the needle essentially at compile time? So we could optimize out the for loop in some way, or just not call it in many cases. And we can do some kind of a heuristic that will help with that. So let's assume that all the needles that we're going to receive are 4 characters in length or longer. What we can do is we can compare the first 4 characters of every letter, and only if they match, we run the second for loop that will compare the rest, no matter how long the rest is. So essentially, this heuristic will reduce the number of times that the inner for loop will be called by comparing the first 4 characters. And the first 4 characters, how many bytes they will take if we're using ASCII strings? This is simple.
4 bytes.
Yeah, 4 bytes. And what is the most common 4-byte type in the computer? Yes, but if we're using more like stricter typing, it will be U. Yes. It's the second one. After this talk, he'll go to dentist, I guess. So let's see how it works in real life. Looks complicated, but it's worth it, trust me. I've made some of the names kind of confusing and shorter just to fit on the slide, because otherwise it's just too long. But what we do, we take the suffix, which is essentially a string view, and we separate it into two parts. The first 4 bytes go into Uint32 variable called prefix and prefix. And the rest of it, we actually just cut away the first 4 bytes, and we end up with a pointer that is called end suffix pointer. So essentially, we have the same for loop. We go over the string. We first compare the first 4 bytes as a Uint32 comparison, and only if it matches, we compare the rest. This looks like over-engineering, right? Why would we do that? And like, this is what we have. So essentially, we take, if we compare banana and apple, we take the first 4 letters of banana, which is banana, and we compare it. If this matches to apple, then we compare the rest. Here's what we end up with. Just one dumb idea, comparing the first 4 letters first, jumped from 500 megabytes per second to 2 gigabytes per second. Across the board, we see 3x to 4x performance improvement with just this tiny stupid heuristic, with all kinds of different strings, randomly generated. Cool, right? Can we do better?
Also, you can do that for 8 bytes.
That's the next slide. Yes. Here we end up with SIMD computing. So SIMD computing is hard to implement when you have variable-sized elements. But what if we can compare 8 32-bit integers at a time and reduce the scope of substrings that we will end up comparing in terms of the suffixes? So to do this, let's introduce assembly, or do it indirectly using compiler intrinsics. So what we can see immediately, when we set up the end prefix, in the past we just had Uint32. Now we take a Uint32 and we broadcast it into 8 slots. So essentially we end up with an M2056 bit value, a buffer, that is filled with 8 identical prefixes. We'll go deeper into those things, through those things, but this is essentially the same variable initialization part. The main for loop is not passing 1 character at a time, but it's passing 32 characters at a time, because 256 bits is 32 bytes. So we jump across 32 bytes at a time. But within those 32 bytes, as we compare 4 byte prefixes, we have 4 different offsets at which we can compare 256 bits. So essentially, we compare to the first letter, to the second, to the third, and to the third. But everything that goes after that has 32 times periodicity. So that's why we have 4 different mask calculations. And if those masks match, then we do the simple for loop of comparing the strings if the masks match. But let's go one by one and make it simpler. What is this? This is essentially the same as saying we have a 32-bit integer.
One question.
Yes.
These instructions and intrinsic instructions, it is just inline functions, or it is just something more than inline functions?
This is a function that is not just inline, so you will not have this function in your assembly specifically. Like your compiler will actually know how to replace this line with his own understanding of assembly. The point is that this is a more fine-grained control over vectorized operations in the computer. So essentially this operation, the very first one, is very simple. We just initialize 8 needles instead of 1 needle. And instead of taking the entire needle, we just take the prefixes. So instead of zeros, we'll put the first 4 bytes of every single of our needle into every single slot of this small compile time known array. What do we do next? So let's take this part now. we've already seen this line before in the very beginning. Does anyone remember what does this function do? Yeah, precisely. So we take the A0 and B0, we compare them pairwise, and we end up with another array which is called matches. But instead of matches, in my code I call it H1, essentially a mask of matching to the haystack at an offset 0. So other than that, we'll have 3 more versions of this at different offsets. What else we can see here? What's the next unique intrinsic? This one, the OR intrinsic. This is just a very simple logical OR operator, and we call it twice. So we have to merge 4 bitwise masks into 1 to understand if there is any match whatsoever. Done. And there's the move mask. So you see we have an if statement, if mask matches, if the mask is not a 0, then do the basic string search within this 32-byte scope. We cannot just pass an M256i into this because an array structure is not convertible to a Boolean statement. So we need some kind of a move mask operation that will reduce those 256 bits into a Boolean statement by sampling 1 bit out of every 32 bits within our 256-bit array. That's it. That's just the rest are just simple for loop within this specific part of this window of 32 bytes, which we run only in very, very few cases when we've matched using the SIMD instructions. If we've matched the prefix with the SIMD, the rest will be done by the computer with a simple naive brute force approach. What we've achieved. Just 1 second, I'll introduce the numbers. We've had 3 gigabytes per second. We've simply added 4 or 5 lines of SIMD intrinsics. Almost no one does this. Almost no one knows how to do this. But this is public domain knowledge. You can just open Intel's documentation, look up the names of the intrinsics, and your software will work not just 3 times faster than this naive heuristic, it will work 8 times faster than one STL does. And for countries such as Armenia, this is crucial for us to know those things. We cannot compete with markets such as India by producing, let's say, 10 million software developers next year. It's literally impossible because we have only 2 million people in our country. And obviously, we cannot just all work as software developers. So we must compete in terms of quality. We must have developers who know this stuff so that we have the best software in the world that has not only 8 times higher performance than what standard library offers, but also it has much higher energy efficiency, and we'll talk about this later as well. So imagine having a data center that is processing 10 times more than a data center in the US. This is essentially having $100 million worth of infrastructure that is comparable to $1 billion infrastructure in the US. And if we can provide this value, if we know those things, we can actually reserve for ourselves this position of the best software developers and computer scientists in the world, people who are not just ready to use basic algorithms and whatever is included into the standard library, the people who are ready to design new algorithms and also implement them in the best possible way. Because there are just the same basic people designing compilers such as LLVM, Clang, and GCC. Those are the basic same normal people in the standards committee from Google, from Facebook. Those are not some kind of amazing engineers or geniuses. Very far from it, to be honest. Those are normal people, and we can definitely compete with them. And if, let's say, a guy like me can just develop something like this in his free time while traveling the world, a team of developers, especially on a payroll, who receive a salary for doing this, I'm doing this for free. A team of developers can do this for sure. And your question?
Yeah. So these intrinsic functions, they are processor specific.
Yes.
Yes. So can I?
The right questions are even more important than the right answers.
For example, I have GNU compiler, just GNU C compiler or C++, and I want to use just the same intrinsics on my, for example, Intel i7 and or my, for example, ARM processor, my Raspberry Pi processor. Is that possible?
No. And this is precisely the reason why this slot is empty. So IoT devices generally don't use very hard to implement and expensive Intel and AMD IP. Like they don't implement the x86 instruction set, and SIMD instructions, such as the same way as any assembly, is hardware specific. So if you want to do this kind of things, or even better, that's the next slide, you will have to take some time and develop 3 versions of your code. The first one that runs on any kind of hardware using just generic C or C++. The second one that will run on Intel, and the third one that will run on ARM. It sounds like a lot of work, but trust me, it is not. I fit databases, machine learning, encryption, and like almost like a level of compiler kind of stuff into 200,000 lines of code and a ton of algorithms that I invented myself in the past 5 years in 200,000 lines of code, while something like TensorFlow, which only does machine learning, so maybe 10% of what I do, but they do it in a much more generic way, to be honest, but still, they do 10% of my workload, and they take 1.7 million lines of code. Mine is 20,000, so it's essentially 10 times smaller, but does 10 times more different things. So compactness and readability will not be sacrificed that much. So let's continue. Let's speculate a little bit. How many of you know what the speculation in a computer is?
Like prefetching and stuff.
Yes, prefetching and stuff. Unfortunately, I don't have any more bounties, and I guess you already have to book an appointment with a dentist, so I'm not giving you another one. Prefetching, precisely. So your CPU at runtime receives an assembly code. When you compile your C++ code into assembly, if you look deeply and if your programs are big enough, you will see that the order of assembly instructions is not exactly the same as in your C++ code. So your compiler can rearrange them. But what is more, your CPU can rearrange the assembly. So your compiler rearranges the C++ code into a custom order assembly, and then your CPU rearranges assembly into custom order of execution. So you can never guarantee the order in which the operations will be executed. You can just define the dependencies. So this operation depends on the result of this one, and those should not be violated. Otherwise, you have a very bad compiler. But let's try to see like how far we can go with those kind of speculations. We had this piece of code. It's like 1, 2, 3, 4, 5, 6 lines of code or so. This one is longer, 1, 2, 3, 4, 5, 6, 7, 8. And if you have photographic memory, you understand that this has more instructions than the other one. Can this execute faster than the other one? The answer is yes. So there is this website which is called godbolt.com. How many of you are familiar with it? Nice. Yes. So Godbolt gave us some kind of intuition that if your program produces shorter assembly, it will work faster. And this is kind of accurate to some extent when you work with very basic programs. But when you work with high performance computing and you know your stuff inside out, you can do a better job than just saying shorter assembly is faster. This specific code has maybe 3 or 4 more instructions and complicated instructions than the other one. So this is the previous version. We have 4 times compare equality, 4 times load, 3 times or, and 1 move mask. Here we have also 4 loads and 4 compare equalities, 1, 2, 3, 4. We have 4 move masks instead of just 1. And we have 3 OR operations, just like here, also OR operations. But in this case, they are scalar operations, not SIMD bitwise operations like over the entire buffer. So we have more intrinsics, and we end up with more instructions, but this works faster. Why? What's going on? And the reason is speculative execution. So Our previous implementation is this one, prefixed with AVX2 instructions. AVX2 is the family of SIMD instructions. So SIMD instructions are part of assembly instructions. But then within SIMD instructions, there are multiple generations of SIMD instructions. And the ones that we've seen as of now, until now, all are called AVX2 instructions. For a set of reasons, I guess we can just go over the chronology of naming as a separate lecture or later. But having basic implementation and then the AVX2 speculative implementation, we've jumped from 8.5 gigabytes per second to 12 gigabytes per second on this specific laptop. It is performance per core. So we didn't even start multi-threading. As soon as we introduce multi-threading, we'll have this kind of performance on every single core, and we'll be only bounded by the memory bandwidth of modern DRAM on server architectures. And this is somewhere about 100 gigabytes to 200 gigabytes per second, depending on how many memory channels you have in your server. So you can see 3 more lines over here, and this is where the other families of SIMD instructions come in. So AVX2 is a very cool middle ground, very cool subset of the ISA, which is instruction system architecture. Instruction set architecture. Yeah, right. Thank you. And the problem is that every generation of those updates may include a bigger size of buffers. So obviously, the biggest variables that we work with in normal code are 64 bits, 64-bit integers, for example, or double floats. Then we introduce 128-bit buffers. So this can be probably 2 times faster. Then we've introduced 256-bit buffers in AVX2. This is probably faster than 128 bits. The obvious logic is that we can just grow this incrementally for as long as possible, just making the buffers bigger and our programs will go faster. This is not actually true, very far from it. And there is this part of the ISA that was introduced in 2015, which is called AVX512. It has 512-bit long buffers, and it is an extremely complicated introduction to instruction set. So it is so damn complicated that the company that introduced it to the x86 architecture, Intel, first not only doesn't support it on all of their CPUs, so this computer was bought this year in 2020, and it still doesn't produce the instructions that Intel introduced in 2015. 5 years have passed, their hardware still doesn't support their own software or their own ISA, to be more specific. This is number one. And second, the x86 instruction set is used not only by Intel, but also by AMD. And today, AMD produces the best server hardware on the market. And they publicly stated that they will never support the AVX512. They are not even planning to do so. And in the world of ARM, there's also a set of SIMD instructions, which are called ARM Neon, not AVX or something. They are called Neon. And using Neon, I was able to accelerate the basics code that we had in the very beginning by more than a factor of 2. And this code is not just fast, even though it may look slower than the server or the laptop code, but it's extremely energy efficient. It's so energy efficient that you wouldn't believe. But like, first, let's talk about the speculative execution for a while. This is the front page of the Intel's website for this specific laptop CPU. So if you just open up your computer, you look up the identifier of your CPU, then you go to intel.com and you look up the spreadsheet. There is no information about speculative execution. Okay. There is nothing even about the cache levels. And by the way, how many of you know what level 1 and level 2 cache is? Oh, okay. So there are multiple areas of levels of the cache in your CPU, like level 1, level 2, and level 3, and starting the next year, probably level 4. And Intel only tells you the total amount of megabytes that you have in your cache. Doesn't even say how much specifically on every level, and that's crucial information. So what we can do, we can go to wikichip.org, and we can look up what they know about this specific CPU. And they tell us that there's a 512 kilobit buffer in the level 1 cache, and it's split between the instruction cache and the data cache. And it theoretically tells us that the upper limit for the level 1 cache for instructions that we have is 256 kilobits. That sounds like a lot, but this still doesn't say us how many instructions can the CPU prefetch to execute them out of order. So unfortunately, all of this is private information, and none of the companies such as Intel or AMD will publicly state what is exactly what is their implementation like specifically. So the best I could do is actually go back to old scientific papers like 5-10 years ago about speculative execution and out of order queues queues for out of order execution for CPUs, and how you can implement them in hardware with transistors and semiconductor level stuff. And what they tell us is that the most practical design for this kind of thing is approximately 16 load or store operations. So approximately up to 16 such operations can be prefetched to be executed out of order, which is kind of a lot. But another important thing is that speculative execution, as the term that became very public, but very popular a couple of years ago, when Intel actually had a scandal called the meltdown. They had 2 issues with their hardware. First one was called meltdown, and the second issue was called Spectre. Those are security vulnerabilities. And those security vulnerabilities are caused by speculative execution. If the same core is processing multiple pieces of different programs, and let's say one program can steal data from the caches of the other program. And when they introduced this thing, when the researchers had found this vulnerability, they also stated that there is a patch for this. You can disable speculative execution. And the practical benchmarks had shown that many of the programs became 30% slower. And this is exactly the same numbers as we get by adding speculative execution by our already fast SIMD search. So essentially, doing your program in speculation-friendly manner and not doing it like this is what will cause you about 30% to 40% of performance degradation. Okay, now let's compare x86 and ARM. So I told you that you will need to write 3 programs. The first one is generic C++, second for x86, and the third one is for ARM. And this can seem like doing a lot of unnecessary work, or let's say doing a lot of thinking and researching, but actually this is extremely simple and similar. We have the same load operations, we do the same comparisons. So in here, in ARM assembly, in ARM Neon, it is called the VC equality, and we also pass the 32 here in the signature of the function to actually specify that we want to split this entire 256-bit buffer into 32-bit integers and compare them pairwise. And once we've done comparing, we also combine all the masks with this OR statement, just like here, h any is the same as masks. So we have kind of different variable names, different function names, but the meaning is literally the same. The only difference is probably that ARM is kind of closer to C++ to some extent because they have stricter types. So in here, I'm just saying that this is just a 256-bit buffer. And here, I'm specifying that those are 4 32-bit integers. And there are 4 of them, not 8, because ARM still doesn't have 256-bit support. They only have 128. And this is the energy efficiency I was telling you about. Have you heard that the new Apple Silicon is very energy efficient and very fast, and new ARM computers are great? This is kind of the reason why. So like ARM is closer to RISC architecture rather than CISC architecture. So RISC stands for reduced instruction set, I don't know, capability or something, reduced instruction set, whatever. And CISC is the complex instruction set. And for ages, we've been making our instruction sets more complex and complex. But if you ask the founders of RISC or RISC-V or founders of ARM, the company that is now a multi-billion-dollar company, they will tell you that even though their instructions are simpler and you may need more instruction to describe the same program, but those simple instructions work 3-4 times faster than the complex instructions. There's actually a lot of stories related to this. We can talk about this after the talk if you're interested. But the end result, if we look onto this, if I take my Jetson AGX, I can actually disable some of the cores. In the basic configuration, it has 8 cores here in the middle, and the CPU can absorb as much as 4 watts of energy. So those 4 watts are split between 8 cores. Each of them receives 0.5 watts per core. And the CPU frequency in this scale downgrades to 1.2 gigahertz. So essentially, that's 1.2 billion cycles per second. How much data we can process in 1.2 billion cycles per second? With this ARM Neon instructions, we can do 2.5 gigabytes per second on 8 cores, on each of the 8 cores, while on a server, we can do 10 gigabytes per second on each of the 22 cores. So you could think that this is better, servers are better, but no, IoT is better because we are much more energy efficient. In the IoT case, those 4 watts translate into 4.2 gigabytes per joule energy consumption, energy data processing per energy consumption. And on servers, the same metric is over 2 times lower, 1.6 gigabytes per joule. And this is these numbers are 2 years old. So if you see the process, it's the 12 nanometer TSMC manufacturing process. Today, the Apple's silicon is 5 nanometer. So it has much higher density. Much higher density means that transistors are shorter. Electricity has to travel less space. So it emits less heat as losses. So essentially, your energy efficiency also becomes better. And TSMC is planning to unveil the 3 nanometer plant in 2022. So we can only imagine what kind of new horizons it will unveil for us. So Armageddon is coming. And if you take the MacBooks of this year, and the modern MacBooks are like $900 computers. This is a $3,000 computer from Intel. The $800 computer from ARM with ARM chip, without active cooling, without any fans in it, has higher performance than my computer that is 3 times the cost and consumes 45 watts of energy. ARM computer consumes about 10 watts of energy. So it's faster, but consumes 4.5 times less energy than my computer. So essentially, the new cheap computers by Apple have made the most expensive computers by Apple obsolete. This doesn't even need a cooling system. This is how amazing it is. And with ARM Neon instructions and with using SIMD instructions, we can not only make a software this efficient, we can make it even more efficient than this. So those are the numbers that we've achieved with SIMD instructions. There's also another topic which is called auto-vectorization. How many of you know what pragmas are in code? When you put /pragma, the pragma directives. There are also pragma directives for OpenMP. And just like OpenMP, there are also compiler-specific pragmas for auto-vectorizations. So essentially, the compiler will use those pragmas to insert those things in mnemonics itself. I don't like this approach, but when we did this benchmarking with Intel, the guy from Intel was very curious, so we added auto-vectorization just for comparison. And obviously, it was horrible. So our numberers are 12 gigabytes per second and 10 gigabytes per second. And we were only able to achieve 1.5 to 4 gigabytes per second with auto-vectorization. So there is no silver bullet. If you want to achieve the best, you have to do the manual labor and write the SIMD instructions yourself. So what is the tooling like? What you can use to do this kind of stuff? First of all, it's horrible. It's ugly. This is like from the 2000s, but this is essentially all there is. So Intel produces some of the only software that you can use for benchmarking and for performance profiling of your software. You will open up this thing called Intel Advisor. You will run your software in it, and it will sample the operations and the metrics from the CPU, trying to understand what is going on. So as you can see, it's spotted over here that my software is using the AVX2 instructions. Kind of cool. but not very useful because I already know this. I'm using those instructions. God damn it. So what's useful here? Those two charts. The first one tells us what is the performance bottleneck of our software. We have two parameters here, two values here, memory bound or compute bound. And it tells us that there's a 52% probability that our software is memory bound. So essentially, we've optimized everything there is to optimize in terms of the way our heuristic works, how comparisons operate, and the only bound that's still there is the hardware bound. So the DRAM just cannot supply us with enough data that we can process. And also there's this additional chart that we've reached the DRAM bandwidth and we cannot go beyond this. And this is actually the limitation of the algorithm. So if we open up the second tool, which is not the Intel Advisor, but the Intel VTune, it will show us such a tree structure. And we will see that it's not just memory bound, but also the memory bound is kind of has different types of memory boundness to it. The first one is the level 1 bound, which is the level 1 cache misses or cache hits. And most of the time, most of our penalty comes from the level 1 split loads. Especially when I load 2056 bits of data, sometimes they're properly aligned, but sometimes I have one part of this 2056-bit buffer on one level 1 cache page, and the second part on another cache page. This is what causes the split loads. So essentially, you cannot load the entire pool. You have to discard the both parts and maybe load it from another cache layer or from the DRAM. And just because we are doing substring search, there is no way for us to avoid this. We tried different approaches and nothing works. So we cannot go beyond this. So here's the most important tool, the runtime benchmarking. How many of you are familiar with a Google benchmark? One? Okay, Google benchmark is just like any other suite for benchmarking. The upper part shows what it looks like. So you just register a benchmark, you provide the name, you provide the function that will be called so many times. And then you can also provide something like the minimum amount of time that you want it to run to have some validity. So let's say I run every single benchmark for at least 5 seconds, and it produces me a table of different results. The number of iterations that it will run is also different. It has its own internal algorithm to determine how many iterations is enough to get statistical significance of those results. So this is a pretty bad screenshot. I generally do millions of iterations, but in here, just to get the screenshot, I made it very fast. So it only did 300 iterations, which is not good enough for statistical significance, but you can take those numbers and run yourself, and you will see more or less the same picture. So just to sum up, the tools are the Intel Advisor, the Godbolt, the Intel VTune, and run the Google benchmark. But one of the important parts here is that you should disable the CPU frequency scaling. So essentially, the 2 GHz line that's advertised on your CPU box is not its constant frequency. It can go faster and it can go slower in some cases. And you must disable this frequency scaling so that your benchmark results are reproducible. And now we can get to the most interesting part. This is the part that you will probably find nowhere. Like almost no one talks about it, and almost no one knows this, even some of the very senior developers. Do you have any questions so far? Maybe you have some, I don't know, thoughts?
How do you disable the frequency?
Oh, this is also operating system specific. So on Linux and on Mac, on Windows, you have different system calls that you can make to actually disable it. On Linux, it's much easier. On Macs, it's a bit hard. But if you're doing the CPU frequency scaling, if you're afraid of CPU frequency scaling on laptops, don't be. So this laptop has a, oh, wow. There is a pointing thing here, I didn't know. A laser, I'm like a kid. So this laptop has a 45-watt chip in it. But the thermal solution is not good enough to dissipate all this energy. So essentially, it's operating at lower frequencies that it could have, so it cannot go faster. So if you're doing benchmarking on the laptop, it will most probably operate on the baseline frequency, and it cannot go faster than that. But if I put the same CPU onto one of those desktop computers over there with proper cooling, maybe even liquid cooling, the CPU frequency will go from 2.3 gigahertz to 4.5 gigahertz. And my results can be, let's say, up to 2 times faster. So they will not be accurate. And that's why if you're doing this kind of benchmarks on the desktop, you should disable it. Okay, let's go to the pitfalls, the cool stuff. So this may be a bit ahead of time for you. So if once you start doing SIMD computing and you know more about this thing, maybe in a year from now, you'll go back to this lecture and you will see those cool things and we'll use them to design the best software possible. Maybe for now they're a bit premature, but here's what the SIMD landscape in the Intel world looks like. So as I told you, we hit the wall of diminishing returns in terms of the frequency growth. So the CPUs cannot go faster than, let's say, 5 gigahertz these days, or maybe 7 gigahertz if you use liquid nitrogen to cool them, which is not very scalable, especially in the data centers, not very stable. So what you do, you add more cores and you make instructions more and more complicated so they can process more data per batch, per cycle. So the very first SIMD instructions were the MMX instructions in 1997. So 23 years from now. I was just 2 years old when this thing happened. I didn't know about it, but it was apparently big news. Then came SSE and then 4 generations of SSD. Those instructions focus on, and let's say up to AVX, I guess, focus on 128-bit buffers. With AVX2, we have 256-bit buffers. And with AVX512, we obviously have 512-bit buffers. How many new mnemonics was added? A ton. 46, 60, 70, 10, 20. Sounds like normal numbers, but this is just a mnemonic. A mnemonic is just a name of operation. Add something, multiply something, and if they can add 100 operations every year, it's hard for me to even imagine what those 100 operations do. Like, I only do that many arithmetic operations. Another problem is that once you add new mnemonics for, let's say, AVX512, you also have to support those same mnemonics for smaller buffers, for 128-bit buffer, for 256-bit buffer. So by adding, let's say, 20 mnemonics, they can add 100 instructions. So the current instruction set contains as many, like the full x86 specification contains probably, let's say, 4,000 different instructions, different combinations of mnemonic and registers, CPU registers, and like how they compose together into unique identifiers, etc. So the problem with AVX512 is that not only it's extremely complicated, even for people who do this for a living, but also it's not supported on almost any hardware. Even if you take the different hardware architectures, and those are, some of them are even server architectures, not many of them support the AVX512. Again, it was introduced in 2015, and a 2020 CPU, the highest end CPU, still doesn't support some part of the AVX512. Bad, right? There's worse. So there is not only level 1, level 2, and level 3 caches in the computer, there is also what is called the level 0, level 1, and level 3 licenses for frequencies. And this is what you will probably find only maybe like on a couple of websites around the world. Like, this is like the hidden gem knowledge. Your CPU, when you buy it, comes in a box that says how many cycles per second it can run. Generally, it's somewhere along these lines, 2.2 gigahertz. It means it can do up to 2.2 billion operations per second. If you run it on if you just use one single core out of 14, and if your cooling is good enough, it can grow up to 3.2 gigahertz. Sounds cool, right? But once you use more and more cores, the heat dissipation can, on the semiconductor, cannot be efficient enough to actually accelerate all the cores to the needed frequency. So the frequency, even the boosted frequency, will degrade. If you have, let's say, liquid nitrogen cooling, but you still run simple code on all 14 cores, the best you can expect for is 2.6 gigahertz. Can we do, if you don't change, let's say, the volting or, like, let's say, the BIOS parameters, this is a separate topic. If you use the AVX2 instructions, yes, they process 8 bits of data per cycle, or maybe 4 bits per data, depending on what's the size of the data. But your base frequency and the boost frequency will go down quite significantly, actually. So 400 megahertz, in other words, it's about 20%. So in theory, you can process maybe 4 times more data, 8 times more data per cycle, but you will have 20% less cycles. So you have to kind of include this into your calculations. But with AVX512, it's much worse. And many people have already told about this. So the base frequency can be as low as 1.2 gigahertz. So essentially you process just 2 times more data than AVX2, but your software is not supported on almost any hardware. And your base CPU will be almost, let's say, 40% slower than this one. So there is not much benefit. And this is exactly what we've seen here. So we went from AVX2 to AVX512 to software that is not supported on almost any hardware. And we've already grown from 9.7 gigabytes per second to 10 gigabytes per second. So one of the pitfalls of people who do SIMD computing is that they decide, I will support all SIMD instructions, both 128 bits, 256 bits, 512 bits, but 128 bits may not give you significant improvements in terms of performance, and 512 bits are not supported almost anywhere. So 256 bits on x86 is like the best middle ground. There are like all kinds of different technologies that Intel uses for marketing purposes to describe how they scale the CPU frequency, how it changes. The name changed every year, but it's always something along the lines turbo or speed or boost, like the stupid marketing words that you should never pay attention to. But the end result is that different instructions can operate at different frequencies. And the easiest operations on the computer are something like integer arithmetic for addition, subtraction, and maybe even multiplication in some cases. But actually, when you do SIMD computing, multiplication is still complicated. Division is extremely expensive, so there are not even SIMD instructions for division. So if adding 2 integers on the CPU can take 1 CPU cycle, dividing 2 integers can take up to 50 CPU cycles. That's how expensive it is. So your goal as a high-performance computing specialist is to have instructions that process as much data per cycle as possible, but also don't sacrifice the number of cycles per second. So your goal is to be as high along on this table as possible. So if you can stay within a level 0 frequency license, this is the best thing to do. At this level, you can get 2.2 gigahertz performance. But if you use very, very complicated instructions, such as integer multiplication, you will drop from 2.2 to 1.8. If you do something like floating point operations or modulus division, or if you use 512-bit buffers, your performance will drop even below this to 1.2 gigahertz. This chart may be hard to find on the internet or somewhere else and may not be useful for you right now, today. But over time, as you start working on this, I strongly suggest you return and look onto it. It will save you a lot of time in terms of benchmarking. So what kind of operations you should accelerate with SIMD? What is the #1 thing to accelerate in your software? So I generally do lectures either on math, on GPU programming, or SIMD. So the math part is obvious, design new algorithms. The GPU part is where it gets interesting. It comes to engineering. So you will want to process a lot of data, and you know that GPUs actually have those tiny cores. They cannot do very complicated operations, but they can do simple operations really fast. And you have, let's say, 1,000 of them. So not 10 as on the CPU, but 1,000. So you can get, let's say, 2 order of magnitude performance improvement if you write your software not for CPU, but for GPU. That's why almost all of AI runs on GPUs, not CPUs. But there are several problems with GPUs. If your data is very small, let's say you have 100 data points, it doesn't make sense to run them on 1,000 threads on the GPU because you have less data than threads. The second problem, if you have too much data. So the first one was not enough data, the second one is too much data. If your data cannot fit into the VRAM, the video memory of the GPU itself, you will not be able to, let's say, put your entire problem or your entire data set onto the GPU, analyze there, and return only the end results. You will end up sending the packets back and forth all the time over the PCIe bus, and this is kind of slow. If the DRAM to CPU bandwidth is 100 gigabytes per second, then the PCIe bus bandwidth between the CPU and the GPU is 16 gigabytes in the best case scenario. The third problem is latency. As it's like a separate PCIe bus and the electrical signal has to travel from the CPU part to the GPU part and then back, and you also have to account for the scheduling on the GPU queues and the orchestration, you end up wasting a lot of time just waiting for the results. So what AI people do? AI people would do the following. So you have your neural network design, and you need to train it first, and then you run it. So after you train it, you do the inference. For training, you will do the training on the GPU, because the bandwidth is important. You need to do a lot of complicated operations. But once the network is already trained, you need to do the inference. And for inference, your actual clients will be coming to your servers. They will send you a request, and you need to answer it very fast. Otherwise, they will go to other provider. So once you have this neural network, you will not run it on GPUs most of the time. Once it's already trained, you'll run it on the CPUs. And almost every single backend for inference, so actually when you're using your neural network, will run on the CPU. So you are not wasting your precious CPU cycles and the milliseconds waiting until the GPU responds. Another thing is that floating point operations are expensive on the CPU. So the most basic things you should focus on when you are doing SIMD computing are things that operate with integers, such as encryption, encoding, parsing, databases, complicated set operations, so something like group theory or graph theory, those very fundamental computer science operations. And for those things, the results are just magnificent. Like, you wouldn't believe. Like, there is a guy in Toronto who was like a computer science professor at one of the universities, and a couple of years ago, he designed a library called SIMD JSON, which is just a JSON parsing library that does it with SIMD instructions. And while everyone does it with normal code, he does it with SIMD on every single platform. And he parses SIMD files at 3 gigabytes per second or 2 gigabytes per second, depending on the hardware. This is about 3 to 4 times faster than every other library on the market, even the fastest one. The final result is that JSONs are absolutely everywhere. Every single web API that you use these days uses JSON. It parses it, it encodes some data into it, and sends somewhere else. If you can do it 4 times faster than anyone else, your TCP/IP networking stack just lost one of the bottlenecks, and the bottlenecks moved somewhere down the stack. This is extremely important. Even if you take the code that I showed you just today, if you replace this std string implementation, the find implementation with my code, it will work 4, 5, 10 times faster than the baseline everywhere in the world. And std string search operation is one of the most common operations in computer science or in programming. And you can actually write a wrapper for this in Java, in Python, and in every other language. So most of the CPU time wasted doing string search in the world will be just eliminated by 1 hour talk I just gave you. This is a very easy way to actually reduce the cost on server infrastructure worldwide. let's save some electricity. Why not? So the end result is that let's use 256-bit instructions on the x86. So Intel and Intel and AMD. Yeah, let's use the 128-bit Neon instructions on ARM. And those are like the most practical ones. They also have the scalable vector extensions and the scalable vector extensions too that are coming next year. And they have, they don't have some of the complicated operations, but they have some of the simple operations on the buffers up to the size of 2048 bits. So if the vendor can implement it in hardware, the ARM company will sell them IP to actually implement, to actually have the operations on those buffer sizes. Avoid divisions, avoid modules operations. So let's even return to something like this, to one of the very first, I actually have the same slide at the end. Remember I showed you std unordered set? std unordered set is like a hash map, and first you compare the hash function, then you take the modulus operation to actually understand to which bucket this hash function maps to. This modulus operation will cost you 50 CPU cycles on the Cannon Lake CPUs, which is like 2019 architecture. Because it's expensive, like that's the math to do accurate modulus operation on integers is extremely complicated. You need a lot of transistors, a lot of logic gates, and they do not even always fit into the core part of the CPU, into like some of the primary arithmetical units. They can be like on some other part of the CPU crystal. So it will take both a lot of time in terms of computing it, but also it's not in the very central part of the ALU.
You mean modulus, not XOR?
Yeah, modules.
You can specialize the hash function.
Well, first of all, you can write your hash functions that return your hashes not for one entry at a time, but for 8 entries at a time. This is number one easy thing you can do. But also, you can find alternative ways how to grow, let's say, the number of hash function buckets. So the obvious thing is to grow them as a power of 2. So from 4 to 8 to 16 buckets to 32 buckets. In this case, you don't need to do the modules operation. You can do just the bit mask, just bit masking the hash value and selecting the bucket index with that.
You mean that the assigned overflow is defined?
Well, you're doing something like an overflow, but not. But you are regulating the number of bits you are allowing. So essentially, let's say you run a hash function on an entry. It returns you a value of 128, and you only have 32 buckets. Let's say it returns you a value of 129, and you only have 32 buckets. In order to decide to which bucket you are into which bucket you are putting the entry, you can either run the modules operation, so 129 modulus 32, and you are getting the bucket index. Or otherwise, you can just understand that 32 is the power of 6 of, it's power 5, or power 5 of the number 2. And so you're only leaving the 5 last bits of the number 129, and this only returns you 1. So you're taking the first, or like the bucket with index 1 out of 32. Got it?
But sorry, there is a problem. It's not good to take two
complement.
For example, 32 is not a good number for hashing or 64 because you only take into only some part of
So it depends on what kind of distribution your hash function produces. So, and your hash function is often parameterized over some kind of input random number. So you would initialize your random numbers generator or your hash function with something from the C's random number generator, and only then get the results. But if you know what you're doing, and if you have a special hash function that can provide you with good enough distributions, If you can avoid the modulus operation, avoid it. It's a bad operation. It's a very expensive one. Okay, so this part we've already covered. This we kind of also did, but like we can talk about it more. But my goal is for you to see the benefit of doing this kind of computing, and actually maybe what's the right English word? Motivate, yeah, motivate you to start learning in this direction, so that we have more high-tier specialists. So I've moved and relocated to Armenia just in September, in the very beginning, September 1st. Before that, as I told you, I grew up in Russia, and then I spent 5 years just traveling to every single country I could find interesting on the world map. And I was building this project called Unum, which is like a very broad framework, mostly targeted towards AI. And I plan to work on this for another 25 years. So I've already spent more than 20% of my entire life working on this project. And then 4 years before that, I was doing research in computer science simultaneously with my astrophysics degree. So out of 25 years of my life, my 9 years of my life were either indirectly or fully involved into this project. And I plan to work on this for another 25 years. But now I will build a couple of companies around it. And I want Armenia to be my R&D hub. So for this, I need the best and brightest C++ engineers I can find. People who are extremely passionate about designing new algorithms, implementing them in the best way possible so that you squeeze every single inch of performance out of your hardware. And people who are just passionate about building a project like this in Armenia. So this is also one of the core parts, or one of the core goals that I have. I've registered a company last week in Armenia. I'm also extremely close to renting an office space, and in the next few months, I will also buy a ton of hardware. I'm working on the data sets that are petabyte scale. So no, not a single person in this country, I guess, works with a petabyte of text. Not videos, petabyte of text. And probably there may be 20 companies in the world that can do this kind of stuff and do this in a good enough way.
What kind of text?
So at this point, I work with the biggest data set that exists, the World Wide Web. So I just analyze the entire search space and like build search indices for that. My end goal is to work towards AGI, Artificial General Intelligence. So the next logical step of modern deep learning and AI, or maybe some kind of completely new models, maybe on a span of 25 years, we'll get to this. But as I was building different parts of my system, I realized that the components that I could use to build this AI or just test systems are extremely slow. So I tried using the data crawlers and the data parsers that were designed by other people and in other languages, which was just a complete disaster, like Python, JavaScript. Oh, that's a mess. This is the right audience to say these words. We love talking how our language is better than anything else. So I tried using this. I tried using the classical databases such as Postgres to store the end results, to store the analytics, to have some kind of deep learning framework that uses the database as its external storage base. And it was just extremely painfully slow. And no matter how much hardware I bought to do this, I still couldn't get to the numbers that I wanted. So what I did, I implemented everything from scratch. My own databases, my own compression engines, and this is very early stages of now, it's just prototypes. But I'm starting to collect them together into products. And the very first product will be the Unum DB, the Unum database. There is a website, unum.xyz. And there's also the domain name unum.am, which is empty for now, but I will update everything soon. If you open up the unum.xyz, you will see some of the benchmarks for my database. And mainly I work with graphs and graph databases. So graph database is like the limit to which you can push the relational database. Because everything in a graph database is a relation. Everything is an index. I have quite an extensive set of benchmarks over there that you can look into and understand what I'm aiming for. And tell your friends if they're interested in working in this kind of project. I will be hiring very soon. I guess that's it. What kind of questions do we have? Let's check if there is anything on the Zoom call. Is anyone there? Let's see. Artur, can you help us?
This acceleration all is hardware specific, yes.
Կգաց չատը բացես, դենամ կարող եմ ինչ-որ հարցեր կան։ Հա, լսում եմ անգամ գաց ասում։
Բոլոր օպտիմիզացիաները hardware specific են, թե
So, not all of this is like hardware specific, but most of the benchmarks rely on some parts that are implemented in hardware. So essentially, the Unum DB part is about databases, and databases write stuff to the disk, and disks are extremely slow. So the best way to make it fast, to make a database fast, write less data to the disk and read less data to the disk. So you need a good compression algorithm. Compression algorithms do what? They work with integers to find common patterns and then reduce them. Aren't the integers the best topic we've just covered for SIMD instructions? Yes, integers are the best. So I designed my own compression algorithm, which is not general purpose, it's purpose specific. And as I have my own database, I actually know what's the data layout going to be within this database. So I can design a very specific compression algorithm that knows, that uses my knowledge about how the data is organized on the disk. And I can also implement it in hardware with SIMD instructions. So if you take something like Snappy, which is the compression engine used by almost every single database on the market, and it was implemented either in Google or in Facebook, their decompression speed on my hardware and my data set reached about 2 gigabytes per second. And it's a general purpose compression, probably as good as you can get with general purpose compression. My purpose specific compression decompresses at 7 gigabytes per second. So something that could have been a bottleneck if I used the classical compression algorithm is not a bottleneck in my case, because I have something accelerated with SIMD instructions and something that uses my own algorithm that uses my prior knowledge about the way the data is structured on a disk. So huge part of the benefits that I will get over time developing this framework, Unum, and the products on top of it is the full vertical integration across the stack. So my AI will connect with my databases will connect with my compression engines, and one day my compression engines and everything else will connect with my own hardware. And this is the stuff that companies like Apple do. That's why they have the most energy efficient products. They have extremely high quality products that work out of the box. Now, if you want to design your software infrastructure, you need 20 DevOps guys just to orchestrate all of this and to connect one tool to another tool. And I will also try to be not fully isolated. So I will focus on those kinds of APIs that are easiest to implement and are easiest to maintain. So almost all of those C++ libraries that I develop have Python interfaces and have proper documentation already now. Like, it's very important for me to write good documentation because I have a horrible memory. And as I work on this alone, I return to code over time. And some of the code I wrote like 8 years ago or 5 years ago, somewhere maybe on the Bali or in San Francisco or in Buenos Aires. And maybe I was, let's say, sleepy when I wrote it. Like, I do not remember what I wrote. So I have to make it as easy as possible and as readable as possible so that me after 5 years or 10 years can come back to this and work with this. So I don't want to hire 100,000 people like companies like Google and Apple do. I want to hire maybe 10, 20 people, and avoid maintaining horrible, shitty things like SQL. We'll have just pure Python interface for our main C++ code. I'll let our customers and our own products be built on top of it. And that's the plan. So let's look at the questions. And whoever is still on the chat, if you have any questions, it's the right time to type. Yeah, sounds very similar to GPU, of course. I hope you're going to share the record with us. That's question too fast, guys. I guess they will. We'll probably put it somewhere like YouTube. Any more questions?
About Unum DB, so it's not a SQL database.
No, it is not.
Yeah, so it's what kind of
Okay, so I told you that it's very important for me to have purpose-specific optimizations. So instead of having just one table data structure to fit them all, so everyone can use a table to store his SQL tables. As of now, I have a few different specialized databases, a prototype for table database, a graph database, and a text search database. So essentially Postgres, Neo4j, and Elasticsearch. And for comparison, a Neo4j is a unicorn, Elasticsearch is a $10 billion company, and MongoDB is also $10 billion company, Snowflake is $75 billion. This is a big market, right, for Armenian company to enter. But with this kind of numbers, I guess we can. And for the next few months, my goal, my engineering and R&D goal is to actually find a way to combine those multiple databases into one complete project that it has a flexible schema like MongoDB. So you can just insert whatever documents you have, and it will internally find the best representation for it. But I haven't achieved that so far. That's why I have two parts. The DB scans for Unum DB graphs and the text indexing capabilities of the text database in Unum. Oh, and by the way, these numbers are per core, per single core. I can do this. I have a server with two 22-core CPUs, so it's 88 threads. So I can get to those numbers on every one of the 44 cores, which translates into about 22 gigabytes per second of indexing performance. This means I can index all of Wikipedia in 2 seconds. Yes, and I can index, so at 20 gigabytes per second, the common crawl data set of the web is 200 terabytes. So I would need just 10,000 seconds or 3 hours to index the biggest data set in the world. The one that is 200 terabytes in text. Okay, and yeah, that's it, I guess. I guess, yeah, thank you.
Is there some GitHub project related to this problem?
Yes, so first of all, there is oh, display.
Just to take a look.
So the databases themselves are not public yet, and they will not be. So as I told you that I work with AI and very huge data sets, I can see some strategic value in this, and I don't want to share it with the rest of the world right now. But it's very easy to copy software, and almost every big cloud provider, such as AWS and GCP, they just take open source projects and resell them, taking all the profit margins to themselves. In that way, not only I will not benefit, but Armenia will not benefit in any way. So this will remain a closed source project, but the specific benchmarks and the Substring Search and the SIMD stuff is available over here. I will have, let's say, a small team who will be working on this. Maybe over time it will grow bigger. And if you learn this stuff and if you become a cool HPC guy and a strong AI developer, you can join our team and you'll have full access to the databases and to the AI that I'm developing. Okay, I guess it's time to sum up everything.